get into today's lesson, guys. Today, we're going to be talking about probability identities. Okay, so we're going to be learning about identities and different rules that we can incorporate in calculating for probability. So we're going to do a big focus on probability itself, not so much on sets and subsets. Okay, but before we start, I want you guys to answer this question on the screen for me. Okay, it's a pretty easy question by grade 10 standards. Okay, by grade 10 standards. So I want you guys to have a look at it, answer the questions that have been given over here. Remember, in any situation, we're going to need a sample size. So you guys need to count up for me how much the sample size is, because when we calculate for the probability, that is definitely needed. And when you're done, you're going to put your favorite emoji in the chat. I'm going to put my favorite emoji in the chat. Let me know when you're done. Put that in the chat for me, please. Okay. Go for it, peeps. Okay, so we know that our sample size is 152, and you're going to need that to calculate for the probability. So a survey was conducted amongst learners in grade 10 concerning their favorite color. The results are shown in the Venn diagram. Now, the first question here says, how many learners took part in the survey? Thank you, Kuhle, for giving everybody the answer, 152. Okay, and the way we figured that out is just by adding all the numbers together. Hello, close bracket. Lovely to see you. Okay, now it says, how many learners liked red? So what we're going to do is we're going to count how many learners are in the red. Okay, why am I'm now highlighting it in blue and it looks weird. Okay, let me highlight it in pink maybe. There we go. How many learners like red? We are told that 47. 28 plus 19 is 47. Okay, how many learners like a color other than red or blue? A color that is not red or blue. That's it. Let me see the good. The answer is 63. All right, now it says, how many learners like red or blue? What exactly are we asking for, peeps, when we say red or blue? What do we call this? In probability speak, in mathematical speak, what does or mean? Oh, it's not the intersection, it is the what? Correct, Funzo, that's it. Beautiful, it is the union, right? It's the union, and I'm gonna do it in purple so to show you guys that it's the union of red and blue, right? The union, which means you can like any of the colors, it doesn't matter, both of them. Right, and the way we're going to find that is by adding all of these numbers together. Who said uni something? Okay, so we know that if you like red or blue, we count all of these, it would give us 89. Okay, now, correct, Funzo, excellent. Now, the next question asks us for the probability. Now, remember, guys, when we calculate for probability, the probability of any event occurring is going to be the size of the event divided by the sample size. Okay, that's what we're getting here. So the first question says, calculate the probability, oh my goodness, calculate the probability that a grade 10 learner chosen at random only likes red. Beautiful, nicely done. Funzo, I mean, like, you're answering all these questions for everybody. Nobody else is even getting the chance. Okay, so we want red only. And we know that red only cannot include these people in the intersection because they like both. So red only has to be 28. So that has to be 28 over the total, which is 152. Okay. Now, the next question says, what is the probability that a kid chosen at random likes red and blue? Good. This and tells us of the intersection, which means you need to like both of them. Okay, so only 19. Michelle, I'm going to answer that question in just a second, my sweetie. Hold on for me. Okay, I'm about to show you what I mean. Okay, I will answer that question just now. So we know that's going to be 19, right? So remember, guys, and is the intersection. So we're going to go the probability of red intersection with blue. Okay, because that is and that's going to be 19 over 152. And as Namisile says, that's going to be 0.13. Thank you. Thank you so much. Thank you. Okay, now let's talk about the last one. This says, what is the probability that a student chosen at random does not like red? What is not called? Probability speak, what is it called? What does not mean? What is it called? The what? The something with a C, oh my word. Correct, Imelda. Thank you for putting Danveer out of his misery. It's called the complement. The C what? Guys, the something. It's called the complement. So we want everybody who does not like red. The complement of red, which means we cannot count anybody in red. These people don't count, okay, because they make up part of the red circle. So I'm going to say the probability of red complement, a little apostrophe for red complement, is equal to, now I have to take 63 plus 42, and that's going to give me 105 over 152, which is, according to Namisile, who I'm going to trust with my life, is 0.69. Excellent. Okay, so let me see that question again. Okay, could you please repeat what the base formula stands for? Okay, so Michelle, we're going to break this up into its pieces. So an event is when something happens, when they ask us to choose something at random. Okay, that is the event. Over here, they've asked us to choose at random. What would happen? What would be the probability if the event was chosen that a child only likes red? One of the grade 10 learners only likes red. We know how many kids like only red. That's 28. So the number, this represents the number. How many learners like only red? And the event is them liking red. So the number of events, or the size of the event over the full sample size. Do you see how we call this part S? S is the full sample size. So the size of the full sample. I trusted you. Okay. All right. So I'm hoping that answered your question, Michelle. Okay. All right. Excellent, guys. Let's now continue to what we're going to be learning about today. We are going to learn about the independent rule, the addition rule, and the multiplication rule. And all of these things are going to be telling us something. Okay. But we're first going to see how these particular rules actually work. Now, I'm going to use A and B in order to explain what's happening. I see, yes, the train is moving. You're a little bit late. Welcome to the party. So I'm going to call this part A, and I'm going to call this part B, right? Now, if we're looking at calculating for the additional rule, the addition rule, right? What does this little duty here in the middle mean, everyone? What does that little symbol over there mean? The duty, the symbol in the middle. What is it? What does it stand for? Correct, Danveer, don't doubt yourself. Correct. It stands for union, right? So the union. Now, if we think about the fact that both of these circles have numbers or values or some size of some sort, the union would have to be the whole of circle A, and the whole of circle B. Now, here is the problem, guys. If I decide to put the whole of circle A together with, let me do them in two different colors to show you exactly what I mean. Okay, I'm going to make circle A pink. The whole of circle A, correct, Danveer. The whole of circle A, like that, plus the whole of circle B. What did we notice about both of these? Okay, I've counted a particular place twice. Which part did I count twice, guys? Correct. Good. That's it. I have now counted the intersection 2 times. I've counted it 2 times. So when we look at the idea of the probability calculated for the additional rule, when we have the union, we need to add the probability of the whole circle of A plus the probability of the whole of B minus one of these. We need to minus one of these that we've counted twice. Okay, give me a thumbs up if the idea of the addition rule makes sense. Okay, remember the union is everything all together, but we cannot count the middle 2 times. That's why we need to minus the intersection. Okay, Asbonge, where did I lose you? Don't get left behind. Put your hand up, my sweetie. Let's talk. Okay, so, look, now I'm erasing everything. Let's talk about this. Okay, if I'm calculating for the probability, let's say, for instance, we're talking about the kids up here. Let's look at the kids up here. 28, 19, and 42. Okay, 28, 19, and 42. If I add all of these numbers up, somebody add up quickly for me. 28, 19 plus 42, how much? Is equal to 89. Good, it's 89. Okay, so I'm going to say that my sample space is equal to 89. Now, before we get there, and I'm realizing I may not have mentioned this rule, guys, the probability of all events or everything in the sample space, the probability of everything in the sample space must always equal 1. Okay, and I'm going to give a quick example before we continue. Now, if let's say I flip a coin, what is the probability that I'm going to get heads? Tell me in the chat. What's the probability that I'll get heads? Correct, 0.5 or 1 over 2, right? 0.5. What is the probability that I would get tails? Correct, 0.5 or 1 over 2. Right, now my sample space for this is heads and tails. So if I take the probability of heads plus the probability of tails, the probability of heads plus the probability of tails, that must give me a half plus a half, which is equal to 1. Right, correct, Danvir, that's it. All together, all the probabilities that are possible must give us 1. Kanyiso, let's think about if we have a die or a dice. Right, I know that on a dice, I'm either going to get a 1, a 2, a 3, a 4, a 5, a 6. Now, if I think about the probability of getting a 1, that is 1 over 6. The probability of getting a 2, again, that's also 1 over 6. The probability of getting a 3, 1 over 6. The probability of getting a 4 is 1 over 6. The probability of getting a 5 is 1 over 6. And the probability of getting a 6 is also 1 over 6. Now, if I add up all of these probabilities, how much are they going to give me, guys? Add them all up. Correct, Funzo. That's it. They're all going to give me 1. 1 over 6 plus 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 1 over 6 is equal to 6 over 6, which is equal to 1. Okay, so the probabilities of any event happening altogether needs to equal 1. Hi, Jasmine.
Hi, sorry, but late.
No worries. I'm glad you're here because then you get to do the outro. Because I want you to do the outro. Okay, I'm glad you're here.
So what are you doing today?
We are doing identities. Okay, and we started with the addition rule.
Okay.
Okay.
Thanks.
You're very welcome, my sweetie. Okay, so guys, let's look at this. Let's take this example that I've written over here, and I want you guys to calculate for the probability of A. If we calculate for the probability of A, how many numbers do we have in A? Correct, that's it, Randile, correct. Complementary events add up to 1. Okay, if I add up the probability of A, what am I going to get, guys? Calculate for me. Correct. It's going to be 47, but it's a probability as bonge. So it needs to be 47 over what? Over 89. Good. Right. Now, what is the probability of B? The whole of B. Calculate for the probability of the whole of B for me. How much is that? Correct. 61 over 89. Now, remember what we said, guys. The probability of both of them together needs to equal how much? Together, the probability needs to equal 1. Correct. It must equal 1. Remember, Danvir, it's a fraction. So if I take the probability of A union with B, okay, that's okay. I get what you're saying. The numerator needs to equal 89, correct? So the probability of A union B, I need to get 47 over 89 plus 61 over 89. How much is this going to give me? Put that into a calculator and give me a fraction. Jasmine.
What is 89 equals 5 on the top?
89 equals S,
oh, yeah.
that's the sample
Oh,
size.
yes.
Yes.
Oh, sorry, it looks like a 5.
No worry. Guys, my handwriting is not that bad. Okay, correct. Okay, so many of you will start noticing that the probability of these two things put together is actually 1 over 2. But that is because, or 1,2. But the reason for that is because you counted this part twice. You counted it twice. You counted it when you did this fraction or this part, the probability of B, and you also did it when you calculated for the probability of A. You counted it 2 times. So the only way we can make sure that we don't do that is to minus one of these in the middle. So I'm going to take this and I'm going to minus 19 over 89. Now I want you to put this new part in your calculator. 47 over 89 plus 61 over 89 minus 19 over 89. How much does it give us then? That's it. Namisile, Apiwe, Atlehan, and Melda. Now it gives us 1. Because we've taken away one of the times where we've counted the middle part. Give me a thumbs up if what ma'am has just done makes sense. Okay. Excellent, Funzo. Well done. Good, Atlehan. That's it. Namisile, good, Asmonge. Excellent, Courtney. Amelda, I can already tell you've already got this covered. Love, love, love it. Okay, Asi says, so ma'am, it's like probability of A plus probability of B minus probability of A and B. That's it. And what we've just learned is called the addition rule. Okay, here it is. I've written it over here, right? So the probability of A or B is going to be the probability of A plus the probability of B minus the probability of A and B. That's it. Okay. Ooh, Landile is like, ma'am, this is child's play until we actually start calculating things. And then people will be going, yo, lolo, ma'am is starting again. But I'm glad we are understanding, Landile. Beautiful stuff. Okay, I want to keep these examples here just so we make sure that we are getting an idea of what's happening. All right, that is the addition rule, guys. Now we are going to learn about the multiplication or the product rule. Technically, it's the multiplication rule because product also means multiplication. Okay, so they're probably going to call it the product rule at your school. Okay, this is the addition rule. And these two down here are called the product rule. I want you to write them down, the ones in green, the product rule. Okay. Now, what the product rule does is it helps us to calculate for the intersection. Okay, the intersection. So we're calculating for the probability of A and B. However, there are always certain instances that are going to be different. There are 2 different types of events Okay, I want you to write there 2 events. Okay, 2 events. They are dependent events and they are independent events. Okay, and I'm going to explain with a quick example to make sure that we're all on the same page. Now, let's say, for instance, I have a bag, and in this bag are 2 different types of color sweets. Altogether, I have 10 sweets, right? Now, there are 5 green sweets, 5 green sweets, and 5 yellow sweets. Okay. Namisile, it stands for times, multiply. Okay, it's multiplication. Sorry, let me make that very clear. This is multiply, multiply. Okay, sorry about that, peeps. It's multiplication. Thanks for asking, Namisile. I wouldn't have picked that up. Okay, so let me ask you guys now, what is the probability that I pick out a yellow sweet? What is the probability of picking out a yellow sweet? Five over 10, correct. Or 1/2, right? 5 over 10 or 1/2, or 0.5. Ish, 1/2 or 0.5, right? Now, we're going to call this part event 1, right? Now, event 1. Now, let's say I pick out this yellow sweet, right? And I eat it. I've now eaten it. What's happened to the amount of sweets in my bag? What's happened to the amount of correct? The amount of sweets in my bag has decreased, right? So now I have 9 sweets in my bag. I have 4 yellow instead of 5 yellow. And I still have 5 green. So my question is, which probability is going to be higher in the next example? Which probability is going to be higher, the green sweet or the yellow sweet? Correct, the green. So now I ask you, what is the probability of me choosing a green sweet? What would the probability now be? Correct, Namisile, that's it, Asbongo. 5 over 9. Okay, now I want you guys to note how the probability changed from one to the next. In the first event, my probability was 0.5. That is event 1. In event 2, my probability has shifted. My sample size has changed and my event size has also changed. So we call this a dependent event. Okay. Dependent event, because the probability of this part is dependent on what happened before. Give me a thumbs up if this makes sense. Okay. Excellent. Good stuff. Yes, Asbonge.
Hi, ma'am.
Hello, my sweetie. What's up?
Ma'am, can you please recap for me?
Okay. So if we think about this, let's say, for instance, let me use this example. Let's say you're given a lunchbox to go to school with, right? Inside your lunchbox, they give you a burger and they give you some fries, some chips, and give you an apple, right? Mom gives you an apple to take to school, and they also give you some sour gummies. Right. Okay, pick something to eat, Asbonge. What's the first thing you're going to eat?
Apple.
Okay, good. Now, if we eat the apple, can I eat the apple again? Asbonge, if I eat the apple, can I eat the apple again?
No.
No, I can't. So this event of eating my lunchbox is a dependent event, because whatever I eat first is then going to determine what I eat next. Do you understand what I mean? So as soon as I've eaten the The apple is now gone. I can't eat the apple 2 times. It's gone. Okay,
Yes.
so that's a dependent event. Just like in this example down here, right? If I have 5 green sweets and I have 5 yellow sweets, if I take out a yellow sweet and I eat it, do you agree that the probability has now gone down for me to choose another yellow sweet? Now,
Yes.
there are more green sweets inside the bag than there are yellow sweets. Am I making sense?
Yes.
Okay, great. And that's called, or what kind of event?
Dependent event.
Correct. It's a dependent event. Okay, I hope that cleared that up. Okay.
Yes.
Okay. Excellent. Okay. Namisile, do you also have a question, Masudi?
No, I just wanted to ask your screen.
Yes.
When you draw or write, the numbers and your pictures, they appear when you are done with the statement. Is it me or?
It might be a lag. I think it may either be, no, I don't think it's on my side. My connection is quite stable.
And your
Okay.
speaker, yo.
Yeah, teacher now just give me a thumbs up on your screen if you can hear me in real time.
Yeah, I can. I think there's even background noise from Namsile's side.
Oh, okay. I'm not hearing the background on Namisi's side, but I think on my side, everything is perfect. I think,
Yeah,
you know what it is?
I can hear you
It's just
clearly.
a little bit of a lag on your side. Okay.
Let me get
Okay.
it.
Yeah, try closing your video feed so that you can save bandwidth.
So if you
Namisile.
keep your video feed off, your audio automatically starts picking up a little bit. Okay.
Yeah.
All right. Okay, cool. All right. I'm glad everybody understands dependent events. Let's talk about independent events, right? Let's talk about independent events. Now, let's say I have a coin, right? A coin has heads or tails. What is the probability that I will throw heads? Peeps, what's the probability of me throwing heads? Correct. It's 1/2 or half or 0.5, however you want to call it. Right. This is event 1. Now I flip my coin. I land on heads. And then I flip my coin again, event 2. What is the probability that I'm going to get heads? It's still going to be a half because my, sorry, I'm just trying to see who's unmuted so I can mute them quickly. Okay, thanks, teacher Nels. I know that was you. Okay. All right, so the probability of me getting heads again is still a half. Here's the dumb question. Has my probability changed from one event to the next? No, it hasn't. Teacher Nels, please just check for me. Somebody's unmuted. Okay, somebody's unmuted and it's giving a bit of feedback. All right, good. So because event 1 is no, event 2 is not dependent on event 1, this is an independent event. Okay, independent event. Now, I'm going to explain what this looks like on a Venn diagram, just so we understand the conditions that we're looking at over here. Okay, so if we think of A versus B, right? For an dependent event, what we're basically saying is that in order for A to happen, B must have also happened to an extent because they overlap. Okay, as long as it doesn't matter. You can either write the probability of heads or the probability of tails. It won't change the idea. Okay, it's the exact same idea. All right, so when they say that the probability of, okay, let me not erase that. When they give us this looking thing, this one that goes, probability of B given A. So this little line that they've written here in the middle is called given, right? It's given. What they're actually saying to us is, what is the probability that event B will happen given what has already happened in A? Okay, so what they're saying is, we want the probability of this part first, and then the probability of the rest of A. Okay, let me give a practical example. Okay, let's say, for instance, A and B are, it's Samuel going to a match, right? We're going to call this a soccer match. We're going to call this soccer match 1 and soccer match 2. Okay, now the probability of Samuel winning the first match is 0.5. That's the probability of him winning the match, right? Now, if he wins the match, if they win, right, then only then can he play match 2. And that's also going to give us a probability of 0.5. Now, actually, I'm writing this wrong. The 0.5 should be over here, and over here, the 0.5 should be over there. Now, in order for Samuel to play event 2, in order for him to play match 2, he needs to then have won match 1. Okay, so the probability of match 2 happening is dependent on match 1. Okay, am I making sense? Give me a thumbs up if I'm making sense. Okay, or let me write it the other way around. Okay, I'm going to say 0.5, and the probability of him winning match 2 is 0.3. Okay, so the only way Samuel gets to play match 2 is if he wins match 1. Okay, Atlechan and Courtney, you need to tell me where I've lost you. Okay, so the only way we can actually look at this whole thing being 0.5 is if he's already won the 0.2 part of it. Okay, or 0.3, yeah. Everything, you're gonna have to be a little bit more specific. So don't be a snitch. Don't be a snitch. Guys, it's around dinner time. It's around dinner time. Okay, Courtney, if you say everything, then I'm gonna have to start from the beginning, and I don't know where the beginning is. Okay, I don't know where the beginning is, so you're gonna have to be a little bit more specific. Okay, Atlechan, let's think about this. I'm gonna take my favorite soccer team, right? My favorite soccer team is Liverpool, don't judge, right? So if Liverpool is in, let's say, for instance, the knockout stages of the UEFA Champions League, right? There's a round of 16 first, right? So let's say the probability of them winning the round of 16 is 0.2, 0.2, right? That's the probability of them winning the round of 16. Or let's make it higher, because maybe the team in round of 16 isn't that tough. So the probability of them winning is 0.6, right? Now they've gone through the round of 16, so now they must go to the round of 8. Now the probability of round of 8 is going to get smaller, 0.4, right? So these two events are dependent of each other. Now I cannot have this probability unless we win that game. Okay, so that's what I mean when I say P of B given A. Okay, I cannot find the probability of the second part until I have the probability of the first. Okay, am I making sense, Courtney? So the probability of the dependent event is always, we need to make sure that the first event has happened in order for the second one to happen. Okay, I'm glad you're with me there. I'm glad you're with me. So the only way we figure out what that second probability is only if A has already happened. That's why we're saying, if we want the probability of A and B, we must look at the probability of A times the probability of B, but only if A has happened. That's why we're saying the probability of B given A. We cannot do the one thing without the other thing happening first. Am I making sense? I'm seeing that yes, ma'am. I'm going to take it into consideration as a yes, ma'am. I'm with you. Okay. Excellent. Good. Now, what does this actually mean? I'm going to put the A and the B back in, right? Okay, these numbers are arbitrary. They could be any number. Doesn't really matter. Now, Misila, I'm going to take your question in just a second, right? What that means is, if I have event A that has happened, the whole of event A, the probability of B is not going to be dependent on the whole of A. The probability of B is only going to be dependent on this part of A. Okay, because of the intersection between the two of them. So that is why when we are looking at a dependent event, we look at P as the intersection of A and B. So the probability or the probability of A and B for a dependent event is going to be the probability of the A part times the probability of B, given that they overlap. They must overlap in order for there to be a conditional probability for both. Okay, I'm just going to read Danveer's statement here just to make sure I understand. Okay, so with the coin thing, in order to get heads again, you would have needed to get heads first for you to have a chance of getting it again. Okay, Danveer, in the case of the coin doesn't matter because after I've flipped the coin and I've gotten heads. The fact that heads is there doesn't change. Okay, when I flip the coin a second time, heads is still there. All right. Namisile, what's up?
Okay, I don't understand anything. I'm not gonna lie, ne? Because when you're drawing there, I can't see anything. I think it's because of load shedding. So can I at least explain what I heard?
Yes.
So you're saying, okay, there are two events, those two circles.
Mm-hmm.
And then you're saying A needs to happen so that B can continue or can happen.
Correct. So B is dependent on A happening. Correct.
Yes. So there was where you wrote 0.5, 0.2, and 0.3.
Yes, that was just an example. Okay.
Why?
What do you mean why?
Why isn't it 0.5, 0.2, and 0.5? Or because it's called
The probability of any event altogether must equal how much?
x1.
Must equal 1. So we cannot have 0.5, 0.5, and 0.2. Okay, so all the
numbers that you added. I'm saying the numbers that you did, the 0.5, 0.2, and 0.3, you just wrote those numbers down just in G.
It was just an example in J. So it didn't really mean anything to the example that we're doing here. Okay.
Okay, thank you.
All right, you're very welcome, Ms. Video. Okay, we're gonna have to get into an example, guys. Otherwise, everything we've just learned is going to be a waste. Okay, now I want you guys to look at this statement that I've put over here. This is for a dependent variable. Okay, so what is the probability of A given B? It's going to be the probability of A and B. What is and again? And is the intersection, correct? Divided by the probability of the whole of B. So I want you guys to write down this formula because this is quite important. Okay, it's going to help us to connect that other one that we did at the top. Give me a thumbs up in the chat once you've written it down because we're going to use it. Thanks, Asi. Good. Okay, I'm going to take those few thumbs up and I'm going to continue just to make sure that we're still okay. Okay, let's read this example over here. And this is talking about dependence and independence, right? Read the question we've got here. It says, suppose a box has 3 red marbles and 2 black ones. We select 2 marbles, 2. What is the probability that the second marble is red, given that the first one is also red? So let's look at this probability over here, right? So the probability, okay, we know that our sample size, our NS, how much is our sample size, guys? 5, correct. That's it, Danvir, because there are 3 red marbles and 2 black ones. So our sample size is 5. Now, what is the probability of getting red? Correct. Because there are 3 red marbles, my probability is 3/5. Okay. Now, we want the probability of red given that the first one was also red. Okay, that's what we want. So if this is a dependent event, I've taken out the red. Okay, I've taken out the first red one. So what is the probability? Let me write this properly. This is event 1. In event 2, what is the probability of me getting red again? What is the probability going to be the second time? Correct, Agerang. We've taken 1 out, right? We've taken out the red one. How many do we have left? 4 of them. And how many red marbles do we have left? 2. So the probability of getting red again would be 2/4. Okay, I hope everybody's with me here. Is everybody understanding why we're saying 2/4 the second time? Sure, I feel like this would be easier if we could all unmute and say, yes, ma'am. Okay, cool. Right, now it says, what is the probability of red given that red has happened? Okay, so we're going to say the probability, Anna says, please repeat. Okay. So Anna, event 1 is that we pulled out a red marble. Okay, there are 3 red marbles, 2 black ones. And then we select 2 marbles, right? What is the probability of this, that the second marble is red, given that the first one is red? Now, the probability of the first marble being red is 3/5. Are you with me? Okay, it's 3/5 because we have 5 marbles altogether and there are 3 marbles in there. Good. Now, what is the probability of me getting red again? Now, one of the marbles has already been taken out. Correct? One of the marbles has already been taken out. So we don't have 5 marbles anymore. We have 4. Okay, we have 4. So what is the probability of me getting red again if I've already taken out a red one? Now the probability goes down to 2/4. One of the red marbles has been taken out and there are only 4 marbles left. Okay, I hope that made sense. Okay, we're going to seriously run out of time. Okay, teacher Nels, I just need to double check with you. You can nod your head. Do we have dependence and independence in tonight's quiz? No. Okay, so it would be what? Union, intersection, mutual exclusivity. Yes. Okay. So, so that is helpful because then we won't have to stress about what's happening here today. Okay. All right. Then we're going to talk about independent events, but we've already taken this formula down. We took it down at the beginning. Okay. Right. I need to do this in 3 minutes. Let's see if we can get there. All right. So it says a die is rolled twice, 2 times. So 2 events, right? It says if event A is the first roll and it shows a 6, and event B is the second roll that also shows a 6, are the events independent? Yes or no, peeps? Okay, remember, it's a dice. It's a dice, right? If I throw a dice and I roll a 6, can I pick up the dice and roll a 6 again? Think about that, guys. Right? Yes, I can. Because just because I rolled a 6 the first time doesn't mean I can't not roll a 6 again. I can. Offenses like maybe. Okay, there is the probability of me choosing a 6 again is correct. I can. So the answer is yes, it's an independent event because the probability of me getting a 6 the first time is 1/6. And then the probability for the second one doesn't change. Correct. That's it, Danveer. So if I roll a 6 the first time, there is, remember on a dice, if I roll a 6, the 6 doesn't go away. The 6 is still there. Okay, so I can roll a 6 again. Now it says, find the probability of A and B. And they've given us the formula, guys. So we know that the probability of A intersection B needs to be the probability of A times the probability of B. Now, it's not going to be 6 times 6, Funzo. The probability of A is 1/6 times the probability of the next event is 1/6. We're multiplying, guys. So we multiply the top and we multiply the bottom. So the probability of this independent event is 1/60. Now I'm saying 66, 36. Ma'am, maybe this may be out of context, but is the probability of A given B is equal to the probability of A independent? Yes, it is. 100%. Okay, because if the probability of the first thing happening being based off of the second thing happening, and the second thing doesn't happen, then obviously it's just the probability of the first thing. Okay. No worries. No worries, Danveer. So the answer we're going to get here is 277. All right, we're going to park this.